Okie dokie. Thank you for.
Cornell. My apologies.
Yeah, I'm from Cornell. Yeah, I was good. Okay. So let's see. Right, I'm going to be telling you about infinite dimensional GIT. Geometric invariant theory, and gauged Gromov-Witten theory. Okay, so this is a talk. This is a talk that I've given several times before. There have been, developments. In fact, I gave a talk about this a few years ago at the ICTS, but there have been some developments. So I'll discuss some of the new things, but also the audience is different, so there'll be quite a bit of overlap from my talk a few years ago. But it's yeah, we've been able to do a lot more recently. So yeah, the setup will be that G will be a reductive group. And it will be acting on an affine variety. And the moduli problem that I'm going to be telling you about is the algebra geometric version of gauge theory with matter. Oh, right, let me see. Sorry. So it's going to be maps. So this is gauge maps from a smooth projective curve C to X. And oh yeah, I should say I'm working over, just for simplicity, I can work over a field of characteristic 0, working over C. The actual paper kind of works in maximal generality, so over a Noetherian base scheme, but for a lot of the results, but working over C just for simplicity. So technically what this is basically it's the stack that it's an algebraic stack. That's how in algebraic geometry, that's how we think about moduli problems. And it's a stack that parameterizes a principal bundle over the curve. It's a G bundle and a section of the associated fiber bundle. So section U. And there's natural notion of families of such things. So the goal of the talk, or the goal of the project, is to basically study the structure of this problem. So, I mean, the technicalities of stacks are not going to be important, although that is the language that we use to do this. Hold on a second. Yeah. So, yeah, the reason why we're thinking about this, the motivation, is basically this is a fundamental interest. This is sort of a fundamental question in modular theory. Bun-G, which I'll explain, the moduli of vector bundles over a curve is obviously very important in many branches of mathematics and in physics, and this has a beautiful structure. which I'll recall in a second, but the structure that I'm thinking about is what's called the Harder-Narasimhan stratification. So I'm gonna, but this structure is missing. The analogous structure is missing. Or I mean, was missing. We feel this is the project is to extend this structure. And when I say it's a fundamental question, so Bun-G is C is the simplest moduli problem that you might think about, one of the simplest. And then the next simplest would be just to add a section of associated bundle. But actually, this comes up quite naturally. So it comes up it's related to. So you can construct. You can construct enumerative invariants. This is related to the so-called I function. You can construct enumerative invariants that are related to the Gromov-Witten invariants of the GIT quotient. Or I should say, if I take, if I take a GIT quotient with respect to some parameter, some GIT parameter, I usually denote my characters chi. So this is one of the motivations why this thing has been studied quite a bit, especially from the perspective from the symplectic geometry community. The idea is to construct using gauge theory a kind of Gromov-Witten invariant, or a different alternative to Gromov-Witten invariants that then you might be able to relate to the Gromov-Witten invariants of the GIT quotient. And this has actually been accomplished quite a bit in the work of Woodward and Gonzalez. So that's not actually the motivation that I want to emphasize today. For me, this is just it's just something that comes up in lots of examples. So let me give you an example. It comes up a lot. So this is the example to keep in mind. So I should say that basically all this is joint work. With my former student, Andres Hernandez Herrero. Okay, so the example that I want to keep in mind is the following. It's what I call the moduli of torsion-free algebras. Oh, I might get back to this in the end, but regarding the I function and these gauge Gromov-Witten invariants, one of the main applications of this structure that we're developing will be to give very explicit computations of gauge Gromov-Witten invariants. So there are actually applications to enumerative geometry, but the thing that perspective that I want to emphasize today is why you might just care about this just as a question in algebraic geometry. So you have the moduli of torsion-free algebras. What do I mean by this? I mean it's a vector bundle. A over C, and a multiplication map from A tensor A to A, and this is a multiplication map, and then an identity section. satisfying the associativity, associative and unital. So this is the thing that you might care about as an algebraic geometer. You know, for instance, Azumaya algebras are, you know, are an example of this sort of thing, and you know, that you can think of this as a non-commutative non-commutative curves with a finite map to X, no, to C, maybe. And the reason being, if you have a commutative curve, C prime, with a finite morphism pi to C, then this is basically the same thing as giving the commutative algebra. If I take pi lower star of OC prime, this is a commutative algebra. As long as C prime has pure of dimension 1, this is a commutative locally free algebra. And this is actually this is a bijection. So in some sense, you can think of this as like a, and you know, there's a stability condition in the commutative setting. There's a stability condition, which is just, if you just say that C prime is reduced, for instance, that gives you a nice stability condition, and the resulting moduli problem has a moduli space. That's a compactification of what are called the Hurwitz spaces. Which is just the moduli spaces of branch covers of the curve C, smooth branch covers. And so you can think about, you can now return to this problem and say, well, you know, this non-commutative curves, or equivalently, these coherent locally free algebras, you know, I can ask, well, do they have moduli spaces? And the answer is no. It's not totally easy to write down, you know, a requirement on the algebras that gives you a compact moduli space. But using the theory that I'm about to describe to you, actually, you can put a stability condition on it. There actually are many stability conditions, and you know, but one of them, the easiest one, the closest one to what I just wrote down for the commutative case, involves saying that it's generically, it's an Azumaya algebra. Generically, it's a matrix algebra, and then there's an additional stability condition, which is a little bit like the stability condition of which is somehow related to stability of the underlying vector bundle, semi-stability of the underlying vector bundle. So, and then with this semi-stability condition, you actually do get a compact moduli space. So okay, so hopefully this is the kind of thing where you're like, okay, like I can see why this particular moduli problem might be of interest, but this is actually an example. Why is this an example? So if I let X, if I let this be the subset of HOM of V tensor V to V times V itself. So I can think of a multiplication as living in here, and a unit as living in there. And so this is X is cut out by some polynomial equations. This is cut out by associativity and sort of the unit identities. Then the moduli of locally free algebras is just equivalent to the mapping stack from C to X mod GL of V. I say this is of rank V is the vector space, and it's not too hard to see this equivalence. So it's the GLV bundle is A itself, it's the vector bundle, and then the section is defining the product and the unit. So actually, this is an example of the kind of moduli problem that I'm telling you about. Okay, so right. So let me just very briefly. So what structure are we looking for? So we'll start with the example for vector bundles on a curve. Vector bundles of rank R and degree D. On the curve C. So for this moduli problem, there's the Hardy-Narasimhan theorem. Well, I should say, before I state this, so right, so a vector bundle on a curve, you can think of it as two topological invariants. It has a rank and a degree. So I can plot the degree on this axis and the rank on this axis, and then every vector bundle in this case, okay, dr. So if I have a vector bundle for locally free sheaf on the curve, it sits. Its topological type is a point in this space, in this two-dimensional space. And if I have a filtration, and let's say E2 inside E1, inside E0, which is equal to E. So if I have a filtration, so I can plot this. I can plot this. So here would be E2, here would be E1 on this curve. I've drawn it in this nice convex way, but it doesn't have to be. I mean, E1 could be, E1 could have been way down here. For a general filtration, I could have had something like that. But the Hardy-Narasimhan theorem says and actually I'll put Schatz and maybe others, maybe Seshadri, and maybe Mumford. I mean, if you could, there's like basically, I'm going to smush everything about this moduli problem together into one theorem. And so basically, every bundle has a unique convex filtration, where convex means the way of the black line above. When you plot it out, it makes a convex arc in the plane, whose graded pieces, whose associated subquotients EI mod EI plus 1 are semi-stable. And semi-stable just means if there is no filtration, no sort of non-trivial convex filtration. So if there's no subbundle whose point on this curve, if there's no subbundle that lies above the line from the origin to E, then you call the bundle semi-stable. So in some sense, as a convex filtration, it's as big as possible. But the uniqueness is quite remarkable. It's just there is just only one. And then also the part that's due to Schatz is that this is basically the moduli problem. Oops. Is that there's a this stratifies the moduli problem. So this on RD, so it's like a union over some indexing set of strata S alpha. So here alpha is literally the shape of the polytope that you get. So I can look above and say, I can think of this as alpha is literally this polytope there. That's what indexes the strata. So it's convex polytope whose lower line is just a straight line from the origin to E. And I'm thinking about the degenerate case is just where the polytope has no area. It's just a straight line from the origin to E as one of these alphas. So it's the shape of the polytope, the so-called HN polytope. And each of these strata, these all fiber over some moduli space of semi-stable bundles. So these are all bundles semi-stable of shape alpha. So this is the moduli of semi-stable graded bundles. So the fact that you get this stratification is what's due to Schatz, and each of these so in other words, Bun alpha semi-stable, if alpha is this polytope, it would parameterize triples, in this case, for this example, triples of vector bundles, namely E2, comma, E1 mod E2, and E0 mod E1. And these are three semi-stable bundles of different ranks of degrees. And the ranks of degrees you can, so that moduli problem of tuples of semi-stable bundles of different ranks of degrees has a good moduli space, has a projective good moduli space. Okay, so this is what somehow the example of like a completely solved moduli problem in algebraic geometry. So, you know, it's too much to hope for that Bun RD actually has a moduli space itself. It's just way too big. It's not bounded. So there's no actual finite type scheme that parameterizes all isomorphism classes. And it's like sort of horribly, you know, it's very extremely non-separated and things like that. So the full stack itself has some sort of issues, but there's this kind of beautiful structure where it's stratified, and each of the strata fibers over a simpler moduli problem. So this map from S alpha. Oh, sorry, I didn't even say S alpha parameterizes bundles whose HN filtration has shape alpha. So inside the moduli of all vector bundles, I can focus on the ones whose Harder-Simon filtration has a particular shape given by one of these polytopes, and in that case, it's a locally closed bounded substack, and if the map that takes a bundle to the associated graded of its Hardy-Narasimhan filtration is a sort of, is a map of stacks to this other moduli stack, which has a good moduli space. So this is like somehow, in fact, a projective good moduli space. So this is the kind of ideal solution that we're sort of looking for. So the goal is basically to extend this to MC of X mod G for general X and reductive G. So yeah, there is basically this framework. So more precisely, what do I mean by this? Well, a filtration in any stack X is a map you think of this as a definition. So I have this little stack A1 mod GM to X, and you see this is a filtration. It's a filtration of the point f of 1 with associated graded point f of 0. So you have if you have a little map from A1 mod GM into your moduli stack, then one is taken to some point. This stack only has 2 points because the GM action is sort of free and transitive on the complement of the origin in A1. So you have the point F1, and then the point F0 has, by definition, a GM automorphism group, and you can think of that as equipping it with a grading. So this is a sort of a general definition of what is a filtration. And so this allows you to formulate. So there's a general framework. So the framework of theta stability and theta stratifications it basically allows you to formulate the Hardy-Narasimhan problem. So formulate the existence and uniqueness question for canonical filtrations. And it also allows you to discuss and a stratification when you have existence and uniqueness of canonical filtrations. You can say, what does it mean to stratify X by the type of the canonical filtrations. So this is a general theory, and this is not a talk about the general theory. So I'm not going to get into it. What I'm going to do is I'm going to translate what it says in this case. So I'll do even better. So in the example, I don't think I gave this a name before. An example of let's say the moduli, I'll call it algebras locally free over C. So this is the moduli of locally free associative algebras. So here's what you get in this example. So a filtration and now I just want to emphasize that this is not a definition. This is actually this is the definition. But if you there's a little exercise that you can do to unwind this definition and put it back into more familiar language, and that's what I'm going to do. I'm going to tell you the upshot of that is that a filtration is a z-weighted filtration of A, and what I mean by this is it's a AW plus 1 inside AW inside dot 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 inside A, and so there are some things that you need for this to be a sensible filtration. You need, you know, AW to be 0 for large W, and AW equals A for small w, and the GER, I'll call this GER W, GW, which is AW mod AW plus 1, is locally free. This is what you mean. This is a filtration in the stack Bun-RD, and you'll see actually. So one thing that's a little different here is that this is not a finite. Is technically this is the same as a finite filtration. I should say this as a finite filtration. So you know A B inside A B minus 1 inside dot 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 inside A0 equals A plus weights, integer weights, W0 less than dot 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 less than WP. And so basically I can think of this, because of these conditions over here, this filtration is basically constant. So AW is equal to AW plus 1 for all but finitely many values of W, and that's what these weights are recording. And so you just keep track of what the actual bundles are and the weights where the bundles jumps. So this is actually more of a parenthetical remark. So anyway, but a filtration is a visual filtration, and the filtration must satisfy. And this is the part that makes it the problem tricky, actually. So it must satisfy, you know, in this case, there's a product structure, and AV times AW has to be inside of AV plus W, and the identity element, which is a global section, has to live inside of A0. And it's this. So if I just said, oh, a filtration of a point here is just a filtration of the underlying bundle, then you might say, well, there's already a canonical filtration. It's the Harder-Narasimhan filtration, but the Harder-Narasimhan filtration does not have to satisfy these conditions. If the Harder-Narasimhan filtration does satisfy these conditions, if the Harder-Narasimhan filtration of the underlying bundle satisfies these conditions, then that is the canonical filtration. But the point of the algebra. But the point is that not all filtrations of the bundles are filtrations of the algebra. And lots of the things that you can do with filtrations of bundles, so in an abelian category, like if I have a bundle, I can just delete a step in the filtration. And if you think about it for a little bit, it's not so clear in this particular problem how you would delete a step in the filtration. You delete a step in the filtration, or no, sorry. Well, yeah, the way that you think about deleting a step in the filtration is I think about two weights. If I think about Wi and Wi plus 1 as sort of coming together, as I move the two weights, they get closer and closer together. And when they are actually equal to each other, that's equivalent to deleting the step in the filtration. So that's actually an important maneuver that you can do. You can simplify filtrations by deleting steps. But in this case, you can't necessarily move weights freely because of these conditions. And so it's not actually clear that I can take two weights of two steps in the filtration and move them closer and closer together and then just delete one of the steps. And so, yeah, it's much harder to work with these kind of filtrations because there's a sort of strange condition. And that's actually what makes the Harder-Simon problem tricky. So the Harder-Simon problem is the following. Let me just say what it is. So for any filtration, f, I can define this number, mu of f, and secretly what this is the weight. It's like the Hilbert-Mumford weight. It's the normalized Hilbert-Mumford weight. So it's like the weight of a line bundle. If there's some line bundle on the stack, and it is the weight of the line bundle divided by the norm, some norm on filtrations. I'm not going to explain what that is, but if you're familiar with like the GIT situation, it's exactly the GIT invariant, but in this intrinsic reformulation. So yeah, so this is like the a filtration is a map from A1 mod GM, so I can pull back the line bundle and look at its weight at the origin, and then there's a notion of normal filtrations. But in this case, it's just a formula. So it's the sum over W and Z of W times the degree of the Wth graded piece minus d over n minus delta. So this delta is actually a parameter that doesn't show up too often in the bundle case, but it's very useful when you have a target x. So it's this formula, and then divided by the square root of the sum of W squared as the rank of GW. So there's this number. This is called the numerical invariant, and the canonical filtration, or an HN filtration. Let me just call it what an HN filtration of a point P is one that maximizes mu of f subject to the constraint that f of 1, the underlying point, has to be isomorphic to P. So I look at all filtrations of P, and I find one that actually maximizes this number, and it's a remarkable thing. I mean, maybe it was known to experts before, but I think I worked it out in my thesis, and also Alfonso Zamora around the same time worked this out, that this this real number picks out the unique filtration, and I still find that very remarkable, because like there's so many filtrations of a bundle. There's not only do you have all the different choices of weights, but you also have all the different choices of subbundles. It's like some kind of uncountably infinite collection of possible ways to filter a bundle. But this one picks out. There's a unique maximizer. So I still find this very remarkable. But you can now formulate this in general for this more general problem, and I put this parameter delta in because it allows you to vary the notion of semi-stability. This is, of course, a special case of a very general definition. And so it's semi-stable we say that P is semi-stable if the supremum of all these filtrations is 0, and otherwise P is unstable. And the question is, does an HN HN filtrations there's existence and uniqueness. I should say that the weights somehow, this is a linear, if you look at this formula, you could think of it as a linear form in the weights. So I've indexed over all Z, but if you think, as I mentioned above, of this as a finite filtration with just and then a finite collection of weights, then you can also write this. It's still a linear form in these weights W divided by the square root of quadratic form in the weights W. And so if you rescale the weights in this by a positive number in this picture, you can just rescale all the weights. That will give you the same value of the numerical invariant here. So I should say that canonical filtration is unique up to this rescaling, up to the rescaling business. So basically the general theory gives you conditions, gives you basically two criteria. These two criteria for a numerical invariant of this kind. To define a theta stratification, to determine i.e. such that the HN filtrations exists and are unique, and plus the if you consider the moduli problem of points in the stack along with the HN filtration, that's actually a locally closed substack of the original stack. So plus this is these stratify the stack. So basically there are general criteria, but the theorem that I'm presenting here, this is the one with Hernandez Herrero, is that the sort of numerical invariance of which I've just shown you an example, but the general formula, there's on this MC of X mod G, there's a class of line bundles that you can consider, and you can define a numerical invariant in this way. So they determine a theta stratification of MC of X mod G such that the semi-stable locus I should say the connected components of the semi-stable locus and the centers of the unstable strata. So that's in this referring to this back to my example of vector bundles in a curve. The strata are these bundles with a fixed Harder-Narasimhan type. By the center of the stratum, I mean this kind of smaller moduli problem that they fiber over, which is sort of the associated gradients of the filtrations. So the centers of the strata, the semi-stable locus and the centers of the strata have proper good moduli spaces. And I should say, in fact, projective. So the stability conditions here are have been studied. So this is previously studied by oh shoot, Dietmar, was it Salomon? I can't remember if it's an A or an O. Doesn't seem right. Anyway, and collaborators. And this is the I mean, they did the GM case, and in general, this goes by the name of in the symplectic world, this goes by the name of Mundet stability. So this is just sort of the usual stability for vortices, and also in the algebraic world, it's studied by Schmidt. And he constructs moduli spaces using GIT. So actually, the stability conditions have been studied quite a bit. What I began by saying is that there's sort of a missing chapter. There's sort of a missing structure, and that is really that these different notions of semi-stability fit together to give a stratification of the full moduli problem in exactly the way that it works for vector bundles over a curve. So I wanted to say a little bit about. I could either say a little bit about how you prove this. So the proof, I'll say a little bit about how you prove it, and then I'll describe something. So I'll say a little bit more specifically, what is the stratification? So the proof, so one step of the proof is a kind of general uniformization theorem. So you can realize this as a sort of infinite global quotient of a generalization of the Affine-Grassmannian by a sort of algebra-geometric analog of the gauge group. So that presentation of this moduli problem allows you to verify one of the two criteria. I mentioned that there are these two criteria for the numerical invariant to give you stratifications. And that is like a sort of purely sort of formal thing. I mean, you set up the moduli problem in this way, you realize that you have it's a quotient of these in-projective in-schemes, and the line bundle that you're considering to define semi-stability is ample on those in-projective in-schemes. And that is actually what you need to verify one of the criteria. But the other one is a sort of, it becomes a sort of, it becomes a large optimization problem. So the question of existence amounts to so basically, right, so for every if I fix my an unweighted filtration, if I fix this, and now I let the weights, I think about the weights as varying, I get some cone. I'll call that sigma A. So it's the thing that's associated. So it's some cone. It lives inside of a copy of RP plus 1, and is just saying this is all filtrations of the underlying bundle. And now if I ask which of those filtrations, well, let me stop here for a second. Let me just pause on this idea. So the function mu is a continuous function on this cone. And basically, the question is, does mu have a unique maximizer on this? And this is for a particular filtration. And so the idea is that what you can do is you can take for every possible filtration, you can take a cone, and the boundary of this cone corresponds to like when Wi is equal to Wi plus 1. And as I said before, then you can just, if you go to the boundary of that cone, you just identify that with a smaller filtration. So if I take all filtrations, each one of them gives me a cone, and I can kind of identify different boundary components of the cone with these other cones, and I glue it together, and I get some huge infinite simplicial complex. It's like locally finite dimensional. The cones are all finite dimensional, but you have a hugely infinite number of them glued together, and mu just gives you a continuous function on that whole large space. And so it's an optimization question, really. It's the question is, does that function on this space have a maximizer? And the thing that makes this question really tricky is that this is the cone of all possible filtrations of the bundle, but inside of here, you have a cone. These are filtrations that are compatible with the algebra structure. So you have this sort of convex, you have this kind of infinite, it's a simplicial, it's like an infinite fan, basically. And that's actually the language that I use to talk about these objects. So it's a sort of formal fan. It's an infinite collection of cones glued together along their boundaries. And inside of that, you have a convex subfan, which are the filtrations that are actually allowable in this moduli problem, the ones that are actually compatible with the algebra structure. And so there's a very kind of beautiful argument, a very simple argument for why the filtration exists from this perspective for the moduli of vector bundles on a curve. It's very different from the classical, for the original proof of Hardy-Narasimhan filtrations uses the fact that you can find the maximal subbundle, maximal destabilizing subbundle, and then you kind of, it's an inductive procedure. But actually from this optimization procedure, there's a completely different way to prove the existence of Hardy-Narasimhan filtrations for the underlying bundle. But the problem is that perspective doesn't actually work when you have this smaller, doesn't actually, the argument doesn't work on the smaller cone. So there's this somehow involved thing where you first compactify X, and in the projective case, you can consider a slightly different moduli problem involving where the curve is allowed to bubble, and then you first show existence of Hardy-Narasimhan filtrations there, and then you use that as a sort of stepping stone to get it for the affine case. So actually the proof of this is somewhat involved. But anyway, this is the kind of flavor of the problem that you end up thinking about. I think I'm sort of out of time, so I'll stop there. I wanted to tell you a little bit more about the actual, right? Am I out of time? Who's the boss here?
You've passed time.
Okay, sorry. So I'll stop there. I'm happy to tell you more about the structure of the stratification if you're interested. I had a little bit of that prepared, but it's fine. Thank you.
All right, let's thank Dan. We have a little bit of time for a short question if we have any. Are there any on the Zoom by chance? Okay, I have a, oh, yeah, we have one from the audience.
It's working. Yeah. So like in the harder Narasimhan, the resulting stratification that can also be done via Morse theory, right?
Mhm.
And so here actually there is a Morse version
Yeah.
by a student of Solomon. This is just a remark.
Oh,
So,
okay.
yeah, he looked at this Morse filtration of these gauge maps, but he wasn't allowing the curve to vary. That's something you are doing. So yeah,
That's
it's
true.
yeah. So it's just something to check if your filtrations agree.
Oh yeah, it's true. Did they do it in full generality? I saw some papers, in specific examples, but I wasn't sure that but yeah, that's the natural question. I wasn't aware that the gauge theory had done it for all
Yeah,
in full generality.
it's pretty general. It's
Oh, okay.
general. Yeah, yeah.
Oh, nice.
It's,
Okay. Yeah.
Samuel Trotwin is the author.
Oh, okay. Okay. All right. I'll take a look for that. Yeah. Thank you. Yeah. Right. And so the curve is allowed to vary here, but it has to be smooth. In the for the there's the next steps of these projects was where you allow the curve to bundle and develop nodes. So you want to extend it over the boundary of MGN bar is a very natural next goal, but that requires some new ideas. There's some sort of technical issues with this infinite dimensional GIT that basically we don't know the correct moduli problem yet. I think that's been a problem for a really long time somehow. In GLN we can do it basically using the ideas of Gauss, we can formulate the infinite dimensional GIT for nodal curves, but in general we just don't know.
Okay.
All right, then if there are no more questions, let's thank Dan again.